Welcome to the inner circle of analytical precision. In our last unit, we introduced the third-dimension molecular shape. We learned that ion mobility gives us a stride or a shadow that mass alone cannot provide. But let's be real. In the world of high-stakes science, a vague idea of shape won't cut it. Today we master drift tube ion mobility, DTIMS. This is the standard meter of chemistry, and we are going to learn how to calculate absolute structural truth from first principles. Imagine you are measuring a diamond. You could use a digital caliper you bought online, but how do you know it's accurate? You'd check it against a primary standard, a reference that is true by the laws of physics. In mass spectrometry, DTIMS is that primary standard. It doesn't ask for a reference, it is the reference. By the end of this session, you won't just be looking at numbers on a screen. You will be the architect of a universal constant that stands the test of time. Today, we navigate 4 strategic chapters. Chapter A, the primary method, why the drift tube is the boss. Chapter B, deconstructing the Mason-Champ equation. We'll turn a complex formula into a strategic weapon. Chapter C, the variable audit, learning why a single degree of temperature error ruins your gold standard. And finally, Chapter D, identifying the known unknown, how to identify a molecule you've never seen before. Traveling wave is fast and sensitive. Trapped IMS is great for resolution. But both have a dirty little secret. They are relative measurements. They require you to run a calibrant to teach the machine. Drift tube is different. Because it uses a perfectly uniform electric field, the math is linear. It calculates the collisional cross-section, CCS, directly from the physics. DTIMS is the only method where the result is a primary property, not just a library match. This formula is just a description of a sprint in a wind tunnel. Look at the variables. We have charge Z, buffer gas density N, and temperature T. When we measure the time it takes an ion to cross the tube, we aren't just looking at a stopwatch. We are balancing these forces to find the CCS, the fundamental shadow of the molecule. A specialist verifies the N and the T because they know the math only works if the environment is perfect. Think of it this way. If you know exactly how long the track is, exactly how strong the wind is blowing, and exactly how much the runner weighs, you can calculate the runner's drag perfectly. That is the CCS. But if the wind speed changes by 1% and you don't notice, your drag calculation is a lie. This is why DTIMS hardware is built like a vault. It is designed to keep those variables rock steady, so the math remains fundamental. The difference between a specialist and an operator is humility before the sensors. Did you know a 1 degree Celsius error creates a 0.5% shift in your CCS? In the world of isomers, that's the difference between a safe drug and a lethal impurity. A specialist audits the sensors and ensures the helium or nitrogen is pure. If there is 1% oxygen in your buffer gas, your gold standard becomes fool's gold. To be an elite specialist, you must also understand T0 correction. The time your ion spends outside the drift tube, in the optics or the mass analyzer, must be subtracted. We do this by measuring the drift time at multiple voltages. The slope tells us the mobility. The intercept tells us the dead time. If you ignore the intercept, you are measuring the machine, not the molecule. A specialist always hunts for the T0 to ensure their CCS is absolute. Imagine you find a peak in wastewater. Mass alone gives 10 candidates. You don't have standards. In 1D or 2 DGC, you're stuck. But we use computational CCS. We predict the CCS for those candidates. Because DTIMS is fundamental, you can compare your calculated truth to the theoretical truth. If candidate A predicts 145 and you measure 144.8, you've made a high-confidence ID without ever buying a standard. Have you ever found a result that matched a library but still felt wrong? A specialist doesn't just match, they prove. By using drift tube IMS, you provide a layer of evidence independent of chromatography. You are saying, the physics of this molecule's shape dictates it must be this structure. That level of certainty is what gets papers published and what keeps your lab at the top of the food chain. Summary, the physics of truth. We've moved from the gym to the factory, and now we've reached the standard. You understand that DTIMS is the primary method because it relies on the Mason-Champ relationship. You know the cost of a 1 degree error. Carry this mantra. Precision isn't a knob you turn, it's the integrity of your sensors. Master the physics, and the truth will follow. You've mastered the absolute math of the drift tube. It is perfect, but it can be slow. Sometimes, you have 1,000 samples, and you need to surf instead of measure. Join me in our next unit, Module 4-7, Surfing the Wave, where we master traveling wave IMS. We're going to trade a bit of that absolute math for extreme sensitivity and high-speed separation. The race is getting faster. I'll see you at the starting line.